Namaste to everyone. I welcome you all in my YouTube video channel. Today, I will deliver lecture on linear algebra, chapter Orthogonal and Unitary Matrices. Lecture number 4, in which I will define and prove the properties of an unitary matrix. Before going to the main content, I would like to give you some basics which will help to understand the main contents. Now we have to remember some important formula. Number 1. Determinant of transpose of a matrix A equal to determinant of matrix A. Number 2. Determinant of conjugate of a matrix A equal to conjugate of determinant of matrix A. Conjugate means if Z equal to X plus IY is a complex number where X and Y are real numbers, then Z bar is denoted by conjugate of this complex number, and this is equal to X minus IY. In the case of matrix, conjugate of a matrix equal to a matrix whose each element is changed into its conjugate. Number 3. A theta. A theta means transposed conjugate of matrix A. This transpose of matrix A and its conjugate. Number 4. Determinant of A theta is conjugate of determinant of matrix A. Number 5. If Z equal to X plus IY is a complex number, and if Z equal to conjugate of Z bar, then Z is a real number. Implies that Z means X plus IY and Z bar is X minus IY. X cancel, implies that 2IY equal to 0, implies that Y equal to 0. Therefore, Z equal to X plus IY means X plus I into 0 equal to X. This is a real number. So Z is a real number. Number 6. Determinant of a Hermitian matrix is always a real number. Hermitian matrix. Let A is Hermitian, then A theta equal to A implies that determinant of A theta equal to determinant of A. Determinant of A theta is conjugate of determinant of A equal to determinant of A. Since if Z equal to Z bar, then Z is a real number. Here determinant of A equal to bar of determinant A. Determinant of A equal to conjugate of determinant of A means determinant of A is a real number. Now I will give you the concept of main content. Main content is unitary matrix. Concept of unitary matrix and its properties. Now we define unitary matrix. A square matrix A is said to be unitary if A theta multiply A equal to unit matrix. Now, I will prove some properties of this unitary matrix. Now, property 1. Unitary matrix is non-singular and it is of unit modulus. Let A be a unitary matrix. Implies that A theta multiply A equal to unit matrix. Implies that determinant of both sides. Determinant of unit matrix implies that it is the determinant of product of two matrices equal to product of determinant of two matrices separately, and determinant of unit matrix is 1. Implies that this is equal to determinant of A conjugate, and this is determinant of A. This is equal to 1. Let this is number 1. Therefore, determinant of unitary matrix is of unit modulus. Proved. Again, from 1 it is clear that determinant of A not equal to 0 implies that A is non-singular, and other part proved. Now we prove the next property. Next property is if A be a unitary matrix, then A theta multiply A equal to A multiply A theta equal to I unit matrix. Now we prove this. Since given that A is a unitary matrix, implies that A theta multiply A equal to unit matrix. This is number 1. From property 1, we have seen that A is non-singular, implies that A inverse exists, multiplying both sides of 1 by A inverse, we get A theta multiply A inverse equal to I multiply A inverse, implies that A theta multiply A inverse, associative property of matrix multiplication. And this is unit matrix multiply A matrix is that matrix. This is associative law. This is A theta multiply A inverse is unit matrix, and this is equal to A inverse. Implies that A theta multiply unit matrix is A theta equal to A inverse. This is number 2. Since A inverse A equal to A inverse equal to I due to property of inverse of a matrix, implies that in place of A inverse we write A theta A equal to A multiply A theta equal to I, unit matrix, proved. Now, number 3 property. If A and B be n-rowed unitary matrices, then A multiply B and B multiply A are also unitary matrices. Given that A is a n-rowed unitary matrix and B is a n-rowed unitary matrix, implies that AB and BA are n-rowed square matrix. Also, A theta A equal to A theta equal to unit matrix, and B theta multiply B equal to B multiply B theta equal to unit matrix. This is number 1, this is number 2. Now, A B whole theta AB equal to, we know this is B theta A theta multiply AB, implies that B theta A theta multiply A, associative law. This is equal to B theta A theta A, again associative law. Implies that AB whole theta multiply AB equal to B theta, here A theta A is unit matrix, using 1, equal to B theta multiply unit matrix is B theta multiply B equal to unit matrix using 2. Therefore, AB is n-rowed unitary matrix, proved. Now BA whole theta multiply BA equal to A theta B theta multiply BA. This is equal to A theta B theta multiply B associative law. Again, using associative law, A theta B theta B A, again using associative law. This equal to A theta B theta B, here from 2, unit matrix. A using 2 A theta multiply unit matrix is A theta multiply A. Here using 1, this is unit matrix I. This is number 3. This is number 4. This is number 5. Implies that BA is a unitary matrix. Proved. Thanks for watching my video. If you are satisfied with my presentation and contents, then please click on like button. And if you have not yet subscribed my YouTube channel, then please subscribe my YouTube channel. Thank you.